first? Is the roof caving in first, or is the magma kind of doing this? And we can discuss this, of course. But because few calderas are super well exposed, people have been turning to all sorts of modeling work, numerical modeling, but also analog modeling. And this is what I'm going to talk about. And here, the point I made earlier, most studies start with this circular approach, assuming calderas are actually circular. And I promise you, in Sandbox, you can make circular calderas. So we started with doing that. And there is previous work by this chap here, Roche et al., and he started to make nice circular calderas in Sandbox experiments some 25 years ago. And you can scale this up. You can then say, depending on the materials you use, you can come up with a little equation, and you can say about 1 centimeter in your experiment, maybe about something like 1 kilometer in nature. So it's a bit qualitative in this context, but people argue scaling does work. And here is a little kind of example. Some of the largest volcanic eruptions we have, supervolcano style, they would be also coming from caldera volcanoes. There's Yellowstone, Long Valley, Tambora, and there you see these have these large volumes. The largest eruption that affected humans is probably the Toba eruption in Sumatra 73,000 years ago, and it had an estimated eruption volume of 2,800 cubic kilometers. To give you a flavor here, there's Mount St. Helens, and Mount St. Helens, the 1980 eruption, had about 0.9 cubic kilometers. And it was a big eruption by our scale. So these caldera volcanoes can grow ginormous, and this is, of course, of relevance. So calderas are often infilled, and they can be infilled by eruptives like ignimbrites, sediments. There can be lakes inside. And very frequently, we have post-caldera activity, resurgence. There's new centers, new volcanoes growing, like here in Aniakchak in Alaska. You see a new volcano growing inside the caldera. So the number of caldera structures and models that has been proposed over the history of caldera research has been quite manifold, and there's different terminology out there. So the simple type, the plate piston type there, is where you have a coherent roof sinking into a reservoir. And then we often deal in nature with a more complicated scenario, a piecemeal scenario. And this is often linked to multicyclicity, where a magma chamber might breathe, it might go up and down, and then you can break up the roof into individual portions. Then trapdoor is when one side of the caldera goes down preferentially, and down sag is when you actually don't have open faults, but you have a depression that's very gentle, and maybe that's an early stage of caldera formation, or as I'll hope to convince you, could also be if we have a very deep-seated magma reservoir. And then very small systems, they have been termed funnels. And this is actually from Japan, but it turns out that this is probably not a type in itself, simply because when you have very small calderas, you fill them in very efficiently. And then it looks like a funnel, but it's actually just a filled-in small version of a caldera. At least that's what we think in most parts. So when we want to model calderas, well, there is a number of things we need to think about, and analog modeling is very visual. So people have turned to this, and there's a whole range of work that goes back to the days when I did that. There's a few more modern papers, but I haven't followed this up in the last little while. I think the results are still very valid. And of course, you can argue there is a lot to be learned when looking into this caldera concept here, and I'm using Harry Potter here to kind of look into the magic and trying to work out how it all works. Some people might argue, oh, analog models, it's very hard to transfer them to nature. And I go, yes, that's true. It's not a one-to-one thing, but I also point out that most of the really good science is very qualitative. There was this chap from England, Mr. Darwin, and he used birds, and he came up with some really good results. So I think we should actually listen to some qualitative approaches here as well. Now, modeling caldera formation, here's very simple things. You can model your magma chambers with different things. We started off with balloons. We made our flat balloons, but you can also use silicon putty and things like that. And one of the important things that we noted very early is if you make a caldera, the main caldera faults are actually outward dipping. If they were inward dipping, you actually get a space problem. It's like a cork in a bottle. You can't push it down so far. So most caldera faults are outward dipping. In the periphery of a caldera, there we get inward dipping faults. They're kind of relaxing and they're allowing these blocks to move inwards. So, and initially, the early workers that mapped calderas, they found these faults. And therefore, very often you see sketches of inward dipping caldera faults. But that's a bit of a legend, and it's an urban myth, if you will. That's not really how it works. It's only near the surface where we have these inward dipping faults. So at depth, we likely have a wider system than the outward dipping faults suggest at the surface. So here's a little caldera that we made in sand, and this is from a deflating balloon underneath. And here you get the main caldera faults. That's the big crack in the center where I have the white stippled line. And then you have the peripheral faults that are kind of more relaxation faults. And this has been witnessed. One of the few real caldera collapses we've seen was Miyakejima in 2000 in Japan. And there we see how these calderas form. We have the inner system that's here, and we have an outer system that's relaxing. So the actual collapse happens here, and this is just sinking in a little bit in order to compensate that the buttress inside the caldera has been removed. So here we are. This is just showing this again. And here's a few more of those images. This is a time sequence that was published at the time. And this is prior to collapse. And this is how the collapse stages go. And at some point in the late stage, you actually lose control over this. This is the funnel idea. There you have so much infill that you actually can't see some of the structures quite so well any longer. So when you think about this, then here's a little summary. This goes back to one of my former PhD students, Owen Houlihan. And so we are starting off qualitatively, at least, with a sagging of the floor, of the roof. And this creates a caldera floor. And then we might have a piston going down. And then eventually we might have eruptions, material being fed up the ring faults and other fracture systems. And when we play this game further, then we get into a very complicated situation in the marginal areas. We may have recycling there. Eruptions can do all sorts of damage and can do, of course, modifications to the caldera wall. So when we do the analog experiments, it's much cleaner than in nature. And the good thing is there's some systematics there. So I hinted at that earlier. There is a caldera diameter plotted here versus reservoir depth. And this is all from experiments. It's not nature. So, and what we see here is that if, for example, we're moving deeper, then our caldera gets smaller and the other way around. And if we have larger balloons, if we have larger magma chambers, then we also make larger calderas. So it's kind of intuitive, if you will, but there is some mathematical rules to this, which is comforting. So this is a very simple and very old numerical model just to make that point as well. So here we have a point source contraction at 5 kilometers depth. And here in purple, we have compression, and in yellow to red, we have extension. And indeed, we see an internal area that is under compression and an outer peripheral area that's an extension. And that's pretty similar to what we see in these analog experiments. Now, these simple early numerical models, they don't allow us to do faults, so you don't see faults, but you can define areas of extension and compression. So the problem, the problem I was interested in was the ellipticity, as I mentioned earlier. Why are some calderas elliptical, and what can we do to make them elliptical? Here, Cerro Galán, one of the largest caldera systems in the world, it ranks amongst the supervolcanoes, and Cerro Galán is some 80 kilometers long and 30 kilometers wide, approximately. It's in Argentina, in the Andes. Large ignimbrites to go with that. And then here's a small example, tiny, less than 10 kilometers, Isabella caldera in the Galapagos. And you would think that on ocean islands there shouldn't be a lot of regional tectonism, but yet again, some of the calderas are actually elliptical. So what does it do? Here's a few more settings or examples. Cerro Galan once more. Santorini here is also elliptical. And even my starting image, Crater Lake, which is the type locality for beautiful calderas, even that is 8 by 10. It's not circular. So what are the possibilities? Now, we're going to discuss a little bit about near-surface structures and topography. Can that cause ellipticity? And then we're going to look at syn collapse regional stresses. Then I'm going to look at syn collapse regional stresses that affect chambers, not only faults. And I took this out because the talk was perhaps a little long, but we can also look at multi-cyclic calderas. If you're really interested, I have the slides at the rear, but then it gets even more complicated. And at the end, I'm going to simulate strike slip systems with caldera formation. So we're making it increasingly more complicated, if you will. And let's start with near surface structures and topography. Now, the question was, what do near surface structures do? And here's the simple experiment. Can't be any simpler than that. We took a knife and we scratched the surface here. So these are just knife cuts about 1 centimeter deep. And we have a magma reservoir, some, whatever it was, 10 centimeters deep. So let's see what happens. So this is the result. And, well, it's pretty circular, but you immediately realize it's getting complicated when you look at the details. Here you have very complicated fault arrangements, and these blocks, they haven't fully detached while others did. So there is an effect, but overall, the structure of the outward dipping system at depth is really not affected. So you get complications at the surface, but it's not a problem for the magma reservoir or the fault structure at depth. So that's the conclusion from this very simple experiment. They remain pretty circular. What about topography? So we went to do a case study in Kamchatka, actually. So here we have several elliptical calderas in Kamchatka, like Uzon caldera, for example, and there's quite some topography. Now, the topography is actually older volcanoes, as we see here in the lower right. There's older cones, and they have been affected by the collapse of the caldera, and then it creates these bulges in the caldera shape. So here's the elliptical caldera, and if you look at it in a different way, if you look at the topography, you could make it even more elliptical if you wanted to. So where's the real boundaries of this caldera, and what does the topography do? These are little cross sections. We don't have to go into detail. They just show the difference in topography, and it's the lines here on that other map. These are the cross-section lines. So quite a bit of steep topography in the caldera margins. So Karimsky volcanic field, similar situation. We have these cones and they partly collapse into the caldera here, for example. And again, we get some very steep topography. We don't have to go into details right now, but how does this work and how does this affect the situation? So these embayments were something we were interested in. And of course, we wanted to model this. So what we did is we made the experiment a little more complicated. We had this balloon again at about 10 centimeters depth, similar to the previous one. We didn't scratch the surface on this occasion, but we put little sand cones on top, approximately where the margins of the balloon would be. And there we can look what the results would be. And here's a little sequence. We started off with this in the top left situation. And here we have our topography. And then we're sagging slowly by deflating the balloon underneath. We're starting to make caldera faults. And of course, they will actually cut some of these cones. And indeed, we made little landslides as well going into the caldera basin. I thought, look, really convincing. And then, of course, we can analyze these results and see what the story is. So when we look at it in detail, we find that there's little graben structures forming in the vicinity of these topographic highs. And then part of this graben structure, in this case, the area labeled here with 2, might actually collapse into the caldera. And this gives kind of faults near the surface on the topographic highs as well. You can just about see them here. So complicated structures, but we're starting to get a sense for it. The translation of the ring fault upwards, as I've shown here with this red line, is really modified in the surface area because of topography, but not really at depth. So again, when you're in the near surface area, for instance, if you're looking for mineralization and faults there, then you might find it's getting very, very messy and complicated with topography. But at depth, the structures tend to be very similar to the qualitative outward dipping system that I mentioned earlier. So you can quantify all of this if you want to. And here again, you have a cone diameter, and we have the opening angle, and there's a systematic relationship. So you can correct for this if you wanted to. If you want to use calderas in Kamchatka for regional deformation studies, then you can actually use the topographic correction we are suggesting here. And this is a useful little tool. You can, in theory, also use this little equation to calculate how tall these cones may have been prior to collapse if you're looking at older situations. So these are useful tools if you want to play with this. And this is with the effect of topography. So here, a little summary. There we can see the outer areas being affected by this. And there, these landslides, they come in. But they follow systematic fracturing patterns that I think we've seen in the experiments. So I'd like to move to the SYN collapse regional stresses. And before I do this, where did I put my coffee? It's over there. Then I'll quickly take a sip of that. Thank you so much. So SYN collapse regional stresses that affect calderas. So here's our experimental setup. And again, it's kind of simple, but it's not fully quantitative. I'm the first to kind of admit this. We had good attempts at scaling, not only my team, but other teams as well. Here's, if you want to read it up, here's the idea how the scaling could work. But I warn that you can't translate it one-to-one to nature, but qualitatively, you can learn a lot from this. And here we designed this little rig, and initially we had hand kind of motion, but eventually we actually had a little motor, and it was more systematic then. But there was a rubber sheet underneath, and the rubber sheet was spreading the entire sand pile. And in that sand pile, we had the balloon. And then, of course, you can see what happens at the surface. So here you can see what the calderas do in a static situation and what they do when you deform while you deflate the caldera basin. So here we have a simple scenario. We're extending, and you can get nice kind of regional extensional faults like a graben system. And then we can, of course, have a caldera forming there as well. So here's our caldera forming while we're extending. And what you note very quickly is there's a major caldera area, but then again, we have peripheral areas here that are affected. And I kind of would draw the boundary here, mildly elliptical, but of course we can argue because the upper part here, if you count that in, then it becomes again more circular, but this may be more of a relaxation, we thought. So here's a few impressions of this. Caldera are elliptical there, and indeed, if you have regional deformation, the ellipticity has a cause from the regional deformation. So if we do no regional forces, as I said earlier, we can make these circular calderas. If we extend, then we do usually make elliptical calderas, but it gets a little bit more messy with the peripheral area here because it doesn't seem to be always present, and actually the peripheral area seems to be stronger in those portions of the caldera that are the wider sides. And here is a compression experiment. We did that as well. And then the peripheral faults don't come out so strongly. They're closed because of the compression. And the collapse is not as systematic. It breaks up more because of the compression again, but you still make an elliptical kind of system. So here's our little sketch, and if you have no regional stress and no distortion, no local stress field, which of course in nature is unrealistic, but in sandboxes you can do that. There you get a certain caldera shape, usually circular, and as I said, depth as a controlling factor on how big the caldera is. In an extensional regime, there it causes the reverse faults to intersect the surface further from the balloon center. And in a compressional regime, it's of course different. There, the compressional regime causes the reverse faults to intersect the surface closer to the balloon center. So you're pushing the shape of the faults inwards in compression, and you're relaxing it in the extension system. And again, you could quantify that if you wanted to, but if you use the analog experiments, you have the scaling issue, of course. So here's a few examples to give you a flavor of how this could link to nature. And I'll take you to New Zealand now. Here's Taupo. Taupo is the source of the latest super eruption. 25,000 years ago, we had the Oranui eruption, 500 cubic kilometers, and here's Taupo. And this is an extensional system. It's a backup system, some people claim, and there's subduction going in on this end of New Zealand, and here we see that there is an elliptical caldera. Some of the calderas are a bit complicated. They're not always super exposed, but Taupo is a classic example, and I felt it was quite convincing. So here's Lake Taupo, and we have this extensional system, and it seems to link with the caldera shape. This is work by a colleague from Italy, Valerio Accocella, and he looked at this in more detail. You can read it up in his papers, but he thinks that it's not only Taupo, he thinks some of the other calderas show this as well, but it's quite green in New Zealand. You can't always see it so well, I think. So we have Taupo, as I said, but there's more examples, of course. I wanted to take you to a tiny example, Nova Rupta, which is more of a crater rather than a caldera. But there we have a compressional regime, and there Nova Rupta is actually squeezed a little bit, if you will, and that would make sense in that system. And Cerro Galan, we said it earlier, it's one of the big whopping calderas, and there we have this kind of system as well. So you can look at this and you can summarize this. There is now a database. Back in the day when we did that work, there was no such thing, but there is now a Caldera database that takes all these things into account, and you can actually link it to the regional tectonic system. And it seems to hold for most cases. So Cerro Galan in Argentina, here it is, and we talked about it for a minute as well earlier. And here the idea is that you have this system, but it may actually spread along faults. So it's not always like that, that it spreads as simple with the extensional kind of regime. But here it seems that we have a complication. It actually goes along the main regional faults. And if that happens, then the simple sandbox analog doesn't really work. If your magma is able to exploit those faults, you may actually make a system that's really the opposite of what you expect from the simple analog models. And there is still a few answers that we are looking for. So this led us to looking at the detailed interaction of regional faults after realizing that not all calderas do what we want in our experiments. And we started off with this. So initially, we did it with sand, but we realized sand fills in very quickly and we couldn't see many of the structures. So what we did is we used a thin layer of flour on top. So the white material here is a very thin layer of flour because it has super high cohesion, and that means you can see the structures much better. So what we see here is incredibly complicated details of how things are interacting. We have regional faults and ring faults, and they are actually intersecting in many ways. So on a local scale, it is really messy. On a larger scale, we still see the caldera structures, etc., but it gets very, very complicated. So syn collapse regional stresses that affect the chamber was the next thing. And this also comes from the realization that Cerro-Golan doesn't always do what we want. And so we looked at how the magma chambers would actually be affected by regional stresses. So we know that fault orientation can be affected by regional stresses in different ways. And here the logic assumption is that magma reservoirs would feel these regional stresses too. So we therefore conducted experiments there using all sorts of things, going back to our little deformation rig there. And we had this basal rubber sheet again, and then we wanted to make magma reservoirs. So we had various things that we injected, and we settled for silicon putty in the end. Later on, I'm going to show you some experiments with cream honey as well. That was a more tasty experiment. And here we had a constant deformation rate. At that point, we actually had a little motor that is doing the deformation for us. And here's the details of what we used in the experiments. So here is an injection of silicon putty into a sand pile without tectonic stresses. And you see a surface deformation. You see a dome that happens at the surface. And because it's low cohesion sand, actually the fractures fill in. Usually you get radial cracks in the vicinity of this, but here they are filled in already. And well, when you dig them out, these silicon putty kind of magma reservoirs, this is how it looks. And it's kind of nice and circular, but the surface is a little wobbly. Here, one ridge stands up. If you want, you could see it as a dike, perhaps, or something like this. But the overall shape is circular. So this is comforting from an experimental point of view. So here's another one, and there you see some of the radial cracks. And here's the dugout system. Again, it's very circular, but there's some spiny ridges coming off, which is maybe not unrealistic. Here's another example just to convince you, and here we see the radial cracks a little better. And this is the reservoir, and here we have one side that even went up, and I can't really explain why it's sometimes on this side, sometimes on that side. We didn't really find a system, but I think it's about maybe there's micro kind of inhomogeneities in the sand pile or so that give rise to this. But here we seem to have a major magma reservoir and dikes coming off from that reservoir. Here's the last one, and there we actually kind of went back to doing it by hand. We were a little irregular there by purpose, and when you do that, you actually also make little dikes, but they seem to be going around. And here's the last one. And here we were super irregular. And there you actually have a whole series of offshoots. It's almost like a flower structure, if you will, with several kind of ridges and at the side as well. And maybe this is the most realistic scenario, that you have a central portion of a reservoir, and then you have offshoots of cone sheets, etc., going from that system. So when we now put this into our regional deformation, here we make our beautiful graben, and then we're injecting while we are deforming. Then we can have a look at this. So here we see immediately that the intrusion of the reservoir actually has an effect. The reservoir is down here, and it's forming at the same time, and you see the regional structures are actually seeing the reservoir. So, and if you dig it out, that's how it looks. So here, the reservoir is actually, like Cerro-Golan, it's parallel to the regional structures. It's not actually pulled in the other way. Here, the silicon putty could, I guess, sense the regional structures forming and was exploiting it. It's not a very pretty magma chamber, I admit, but it does have that shape that really follows the fractures. And this is also why the regional fractures are actually indented here. They seem to go inwards, and that's because the magma reservoir wasn't going the other way as initially hypothesized. This is a huge problem for the Caldera people in Iceland when they do their regional kind of deformation modeling, and that really shows it doesn't work like this. You can't just do it this way. So it's more complicated, and I showed this image a few minutes ago. This is probably what seems to have happened in this particular experiment. So one might expect chambers in extension to be elongate parallel to the extension direction, i.e. if you pull this way, you think they go this way, but it doesn't always happen this way. If the structures are strong, then the magma might actually exploit the regional structures, particularly if they predate magmatism, and then you can have a situation quite the opposite of our initial hypotheses. So I kind of said this, so we can move on. Now, elongate magma chambers. So here, if we have caldera formation superimposed on this, then you can actually imagine how the caldera would look like. So it would actually do the opposite of what we thought. So effects may complement each other, but they could also cancel each other out. So unfortunately, this is not a recipe for success. It just means it can be very, very messy. And each caldera with each of the regional stress fields may actually have their own little system. None of them might be identical to another. So here, another one. Here we are compressing now. So we have regional faults as well from north to south, and we are compressing. And as you can already see, now something else happens. This is where the magma reservoir is forming underneath from injecting silicon putty. And here's our little sketch to go with it. And we have the regional faults with 4, and then we have the affected faults 1 and 2 in the area above the reservoir that's forming at depth. And this is the reservoir that we produced, nice dikes coming off it, but this one worked exactly as we expected. It's squeezed this way and elongate this way, so it would be elongate that way in this diagram. And here it actually worked with the initial hypothesis that if you squeeze it, it will do this. Strangely enough, that actually meant that the experiment we showed with the extension, the experimented compression, produced a similar shape of the magma reservoir. So here's a close-up of this nice little kind of ridge of dikes coming out, and here the ellipticity is quite severe. 1.22 is the aspect ratio. So if you compress, you will likely make very elongate magma systems. So here's a few more of those examples just to give you a flavor. So regional tectonic regimes is a major factor, I think we had to conclude, and it doesn't only affect the faults at the surface and the caldera fault, it already affects the magma system at depth, which then translates into the caldera faults at the surface. So if we have formation of laccolith-style geometries under regional compression without the presence of low competence layers, we haven't even started making the crust complicated, then we get these results. And magma chambers in compression tend to be more systematic. They are perpendicular to the compression direction. In extension, we could have both, depending on how the magma interacts with the regional structures. So caldera formation superimposed on this system, this is what I just said, will then reflect that interplay, of course. So the effects may complement each other, but they may also have the opposite result. So I think we'll skip the multicyclicity, as I said, but the last item I'd like to go through is the regional strike slip systems, non-orthogonal deformation. And there is some big calderas like Toba sitting along major strike slip systems. And this is, of course, also very relevant, particularly thinking about Toba having had a big eruption 73,000 years ago. There's a group of researchers that have looked at DNA studies of humans, and strangely enough, a lot of weird things happened 73,000 years ago. First of all, this is when humans left Africa. The first people leaving Africa that we know of, they were leaving at about 70,000 years ago. And this is also where we had the start of different species. Well, there was lice before, but the start of cloth lice, i.e. these little animals that live in your cloth, that goes back 70,000 years ago. And some people think it's related to the Toba eruption. It got probably very cold. People had to start putting clothes on and things like that. And it's also believed that the human population dwindled to about 10,000 breeding pairs. So there may have been as little as 20,000-ish adult people on the planet. All the others could have died. Some other researchers argue, it's maybe not as bad, but well, what we know is that these large systems, they can be very, very influential for human history, but also, of course, geologically, and they will also have economic aspects that need to be considered. That is the wrong laptop, you're right. Let's use this one. And I promised green honey, the tasty ones. We imported it from France. It's a very special cream honey. It had a certain viscosity and a certain consistency. And we imported large quantities of that, which was good fun. And we had flour there, so you could actually eat the whole thing. So you get tired of it after a while, but it's nice, you know, it's not the gritty sand. And so we had these piles of flour, and we wanted to simulate a granitic system, so we needed something that we could scale, and this turned out to be well scaled. So we have these chambers, and here we did one just for illustration at the margin here. So this is like a cross section. This is how it would look. We have our chamber, and Owen, the PhD student, he put it in with a spoon very carefully. So he was really designing these little magma chambers. And then we had the deformation rig that allowed us to simulate what happens if we have strike slip systems. So here's Owen making one of those magma chambers. And then we had a system like the one in the bottom right, and it's not dirty. We actually sprinkled little magnetite grains on there because the camera that we used would fix these points, and they would allow us to see how the deformation works. So it wasn't dirty sand we used or dirty flour. It was purposefully done with a little bit of sprinkle on top. So, and here is our situation. Here's our strike slip fault that we made. And this is a low opening angle, and it's a brittle crust, and we have no magma chamber in there. So just to test that we can make nice strike slip faults, and we can. So then we can have different opening angles depending on how you design the experiment. Here is one with a little bit of a wider one, 7 degrees, and then you get a graben system in the strike slip area. And now when we look at this one here, this is now with a magma chamber of honey underneath. So we're deforming this, and here's our caldera forming. And this is how the oops, I was too fast, sorry, let me go back. So here we are once more, and this is our caldera forming by withdrawing the honey. And this is how it looks. Not only is the entire caldera system no longer circular, it's actually kind of weirdly shaped, and the magma reservoir can actually feel, the honey could feel the fault. So it was actually deforming. Now this is deflated because we sucked the honey out in order to create the caldera depression, but there you see the fault has clearly affected the shape of the reservoir. And that, of course, is then translated into the shape of the volcanic depression that is forming above this reservoir. So we published this, and we wanted to explain Sumatra, particularly the Toba caldera in northern Sumatra. And the Toba caldera has been described as having formed in a really odd shape. It's very long, it's very thin, and it sits right on the Great Sumatra Fault. That's the Great Sumatra Fault. It goes all along the arc area here. And this is how it looks. And we were quite astonished about how similar these experiments look to the shape of the initial Toba caldera. So we were really happy about this. And it's published in the thesis of Owen Houlihan, and of course in this little paper here, 2008. So Once more, this is our comparison, and I'm really chuffed actually how well this worked. So not only can we make Caldera systems and make qualitative assumptions at least about what happens at depth and what happens at the surface, but we also were able to reproduce this. And it implies that Toba formed in the active system of the Great Sumatra Fault. Magma, the regional tectonics, and the Caldera Formation, they all interact with each other to produce this particular result. So we expect all possible intermediate scenarios, therefore, between these end members that I've shown. And unfortunately, that means calderas can be awfully complicated. And this is the little summary. Elongate, single-stage collapse calderas may result from a complex interplay of a number of factors. And the key factors here seem to be the non-tectonic ones. Topography is important, and this can have a huge influence, even all the way to asymmetric collapse. Then we can have capture of forming ring faults by pre-existing faults. So interaction with regional structures that were already there is important, but also if we have active regional tectonics, this will be felt by the caldera faults and also by the magma reservoir. Distortion of caldera ring faults is a common phenomenon we've seen in the experiments, and this is due to the interaction of the different stress fields. And magma chamber elongation, that can usually work following simple systematics and analogous to borehole breakout, but once you have large regional structures and they are active, then the system may actually be controlled more by the shape of the regional structures. The magma might exploit it, and then these other systematics might not work in the same way. So the above factors can complement each other, but in some cases they can also overprint each other or cancel each other out. And unfortunately, the conclusion is that this is not a simple kind of thing. You need to look at your system individually, and each caldera has a little bit of its own life depending on the magma reservoir, the type of magma, the regional system, and of course also the kind of explosivity of the system, if you will, that will also have an effect. So I'll close here, and I hope I gave you an impression of how calderas might form, what controls them. Unfortunately, there's no simple answer. There's no overarching equation that fixes it all, but I guess you get an idea of the different processes that can play at caldera volcanoes. So thank you very much. And if we have time, I'm happy to answer questions, of course.